up to now, we've seen how this estuarine circulation framework has been is modified in time by different forcing. We saw how the tides modify the estuarine circulation. We saw how wind modifies estuarine circulation. We saw how the fortnightly modulation of tides may affect the estuarine circulation, how river discharge affects estuarine circulation. So now we're going to start talking about bathymetric effects, how the bathymetry affects this two-layer estuarine circulation. And in particular, we're going to be talking about the effects of channels, like you see here in this cross-section of tidal flow, or of instantaneous flow, actually, in Ponce de Leon Inlet, as you're looking seaward. This is depth versus distance, and as you're looking from inside the lagoon toward the ocean, and you see that there are some bathymetric effects, some significant changes in the distribution of the flow. You're looking at the flow there. And then after that, we'll talk about effects of bathymetry, but along the estuary. So up here, when we talk about channels, those are bathymetric effects that cause lateral variations in the flows. And then in longitudinal changes of bathymetry, like seals, you have changes in the along estuary dynamics. So let's start talking about the effects of channels, and we'll spend a good amount of time talking about effects of channels first, and then we'll talk a little bit about the effects of seals. But I suspect that it's going to be a while. It's going to take us maybe three lectures to cover the entire effect of channels. And this is because that's a recent area of research in estuarine dynamics that has produced a lot of very interesting results. And that's my own bias also. So let's first, to understand the bathymetric effects of how the wind might affect the estuarine circulation across the estuary, let's go to a homogeneous semi-enclosed system. So this is not an estuary, this is a basin with homogeneous water. There are no density gradients. So first we're going to see what the effects of wind-driven circulation, how the bathymetry affects wind-driven flow. So in order to do that, we refer here to a paper in 1994. And this is probably when we started paying attention to lateral variations. And if the bathymetry across the channel is flat, like in this case, and the wind is blowing toward us, we're looking into the basin, toward the head of the basin. So this is a semi-enclosed basin, open at one end and closed at the other. And if we're looking into the basin, and the wind is blowing toward us, then the surface flow will come toward us. It will set up a pressure gradient. It will drive the water downstream, so it'll set up a pressure gradient. And that pressure gradient, or sea level slope, will produce a near bottom upwind flow underneath. So that's for a flat basin. So in this particular case, the wind-driven flow will enhance the density-driven flow, right? Because it's acting in the same direction. Now, if we add the effects of bathymetry, and a simple bathymetric variation across the estuary would be this triangular cross-section. If you add that change in bathymetry, so then what you get is downwind flow over the shallow parts of the basin and upwind flow in the deep part of the basin. And you can look at how this arises by examining the dynamics that you have to solve in order to obtain this solution. These are theoretical solutions. In order to obtain this solution is simply pressure gradient balanced by friction. So with the same type of dynamical framework that we have established, pressure gradient balanced by friction, but adding the surface boundary condition given by the wind stress, and then adding some lateral variations in bathymetry, then you can look at the paper to look at how he arrived at this solution. The solution has this shape. And look at it. The maximum flow is given by this quotient that depends on the wind stress, the depth of the water column, and the eddy viscosity, the density of the water and the eddy viscosity. But notice that it has depth variation, so it changes with z, depth, but it also changes in the y direction across the basin. So when you solve this equation, you get this distribution, where the B is the width of the system and H is the maximum depth. So again, this is a solution for a triangular cross-section. And you obtain it simply from that second-order differential equation with the boundary condition of wind stress at the surface, but constraining the solution to a triangular bathymetry. So this is what's called the local wind response. So when the wind is blowing right on the basin, it causes the immediate response, and that's what's called the local wind effect. So the local wind effect depends directly on the wind stress. That's in contrast to the remote effect that is caused by a sea level increase of setup or a sea level set down. Think of what happens outside Ponce de Leon Inlet or St. Augustine Inlet. When you have the wind blowing from the northeast, what happens to the waters in the lagoon there? When the wind blows from the northeast, what do you think would happen? What happens in the coastal ocean? Will the sea level increase or decrease? Decrease? No, increase, right? The wind drives water toward the coast, and it causes a setup. In the same way that when you have westerly winds or southwesterly winds, the sea level gets depressed and you have upwelling. So that change in sea level with time, that's what's called the remote effect. So, for example, think of St. Augustine Inlet, and the wind is blowing off of Georgia, and that produces a setup, but it's not blowing off of St. Augustine. That setup causes a wave, right? It's higher, the sea level will be higher off of Georgia than off of Florida, so that setup will cause a wave that will propagate along the coast, and that's a surface wave, a long wave, and it propagates how fast? Square root of GH. Good job. So it propagates as a square root of GH, and it'll affect the inlet, but it'll affect the inlet in the sense of just an increase in sea level. So you're going to have water rushing in throughout the section. So that's what we see here, that you have water going in everywhere across the section. This is for the case of a setup. If it was a set down, then we'd have water coming up toward us. And for a triangular cross-section, you have the contours of the isotachs distributed like that, with the maximum flow in the middle of the section, and that's because, why do you think that's? Why do you think that you have the maximum inflow right here in the middle of the channel and at the surface? Because of bottom friction, that's right. So the solution for that is given by that expression, and again it's obtained from a simple, relatively simple dynamics, and the flow is proportional to the change of sea surface elevation with time. So that's what the remote effect is. This d-eta dt. A is the cross-sectional area of the channel, and B is the width, the maximum width of the channel, and H naught is the maximum depth of that channel. Okay, so that's what started us thinking about this problem. Us, when I say us, the community. Also, there were earlier papers actually on lakes, but this concept started us making us think about the problem. And another way of looking at the same issue, but now with any arbitrary bathymetry, is represented here as follows. Now keep in mind that the solutions I just showed you are for a triangular cross-section. Those solutions are for triangular cross-section. A more general solution can be derived like that from this momentum balance, which has been non-dimensionalized. So what's that momentum balance? Can you tell? Does it look like something we've talked about before? Probably, I just did this today, so probably you don't have any. So what's that momentum balance? Tricky. Well, I know it's unfair because it's non-dimensional variables, but the non-dimensional variables are like that. U has been non-dimensionalized like that, where U sub D, the subscript D indicates dimensional variables. So this term looks like what term in the momentum balance? What term in the momentum balance has a double derivative of U with respect to Z? The friction term, right? The diffusion term, if you want, or the stress divergence term. So that's what this represents. How about this one? What term in the momentum equation has a slope, a surface elevation slope? Pressure gradient. So we have a momentum balance, same momentum balance that Wong solved. Exactly the same momentum balance. But now this comes from a paper by Weiner in 2004. And by non-dimensionalizing the momentum balance, you can actually generalize the solution, and the solution will not depend on the eddy viscosity and will not depend on the wind stress, because you have a relatively straightforward second-order differential equation that's given like that. So if we use the boundary conditions that there's no flow at the bottom, and that at the surface the vertical shear is given by the wind stress. This du dc equals 1 means that at the surface we have the wind stress. That's because of the non-dimensional variables. So this is well known. We've seen it elsewhere. We've seen it only for a profile, and that's the same thing that Wong solved. But Wong solved it restricting the solution to a triangular cross-section. The beauty of this non-dimensional solution is that, like I said, it doesn't depend on the eddy viscosity nor the wind stress. So if you integrate twice this momentum balance and apply these boundary conditions, what you get is that solution. So notice that solution tells us that the flow driven by the wind has two parts, two contributions. The contribution produced by the sea level slope, the eta dx, and this part, that what do you think depends on this one, which is the wind stress. So this part is due to the wind stress, and this part is due to the sea level slope. Now look at the shape of the solution. It's very interesting. The part that's driven by the wind, it depends linearly on depth. So think about what does the wind do to the water? It drives it at the surface, more strongly at the surface, and then decreasing with depth. So it's a flow like a Couette flow. Remember from your fluid mechanics class, a Couette flow, that maximum at the surface, decreasing linearly with depth. So this is a Couette flow driven by the wind. And this would be, what kind of shape would this be? Parabola, right? So you could have flow going in the opposite direction, even to the wind stress. So the key to be able to draw a solution for this is to determine the sea level slope. So what would you do about that? What do you think you can do about that? So again, all you need to do is to get a solution to the wind-driven flow at any cross-section H. H is the depth of the water column, so you can prescribe H as a function of Y, and you get this very nice distribution of the flows. All you need to do is, you have to prescribe the eta dx, and the depth of the water column, the depth distribution across. Yes, so those are the two things that you need to prescribe. But the distribution of depth across the your channel, you can do it, right, without any problem, because you know it. But how about the d8 at dx? Remember, this is non-dimensional, so you could measure it, right, and non-dimensionalize it, but more fundamentally, you can derive it from the solution up here. And if you define the volume transport as the integral of this solution with respect to depth, so if you integrate this solution from the bottom to the surface, again, if you go ahead and integrate this, what you're going to get is, you're going to get h squared over 2 from this term. Well, from this term you get this h squared over 2 comes from this term, because the integral of z is z squared over 2 from 0 to h gives you minus h squared over 2. But when you integrate this h, it gives you h over 2. So h over 2 minus h, well, if you do the integral of this, you're going to get h squared over 2. And also, if you do the integral of z squared minus h squared over 2, the integral of that, and evaluate it from minus h to 0, you're going to get h cubed over 3. And that's multiplied times d8 at dx. Why are we doing this? Because we need to find out how we can determine d8 at dx. So now if we integrate this volume transport across the cross-section, and assume that there's no net volume transport, so that is, if we integrate this u with respect to y and make it equal to 0, so that's what we have here, where we have non-dimensionalized the y direction of the motion, so make it from minus 1, which is one end of the channel, to 1, which is the other end of the channel, going across it. So if we integrate it across and make it equal to 0, then if you integrate this one with respect to y and then this one with respect to y, what you get is this relationship. You can solve for d8 at dx, and that's simply 3/2 of h squared over h cubed, where h is the depth of the work column, and these brackets represent an average across the section. So it would be the depth, the cross-sectional average of the depth squared divided by the cross-sectional average of the depth cubed, multiplied times 3/2, and that's your value of d8 at dx. So it's relatively straightforward.
You cancel 2 h's out and get 1 h.
Where? Oh, yes. Well, you can do it. I'm not sure if by doing the cross-sectional average you can do it straight like that, because it's a cross-sectional average of the depth distribution. So you can do it straightforward and see if you get the same result with any depth distribution. So this is what you get from that solution. These are beautiful solutions. The solution is right here, down here, and notice that I've noted the depth as a function of y. So the depth distribution for these 4 cases is given by this expression. And you can try to reproduce these results in the comfort of your home, and you'll see, you'll understand better these concepts if you try to reproduce this solution. So all you need to do is, instead of this h over y, this is the h over y, the h of y. So that's the depth distribution. If you define that depth distribution like that in this solution, and solve it for z, d8 at dx, remember, is the cross-sectional average squared over the cross-sectional average cubed, multiplied times 3/2. So with this, again, very simple and elegant solution, you get these distributions. Notice that for a triangular cross-section, you get downwind flow. This would be downwind flow. So again, if we're looking into the channel and the wind is blowing toward us to keep us awake, you'd have downwind flow, that is water coming toward us. Those are the white contours, and the orange contours would be upwind flow going against the wind. Again, this looks like Wong's solution of 1994, right, for the triangular cross-section. Why does it look similar? It has to be similar. I mean, it has to be the same because you're solving the same dynamics with the same boundary conditions. But yet this is a more general solution because you can apply it to any bathymetry. Look at this bathymetry. Then you have downwind flow here and upwind flow there. So you start to have a separation between the downwind flow and the upwind flow. The upwind flow doesn't intrude all the way to the surface. In the case of this bathymetry, a little smoother bathymetry. When the bathymetry is even smoother, then you have more of you have vertical gradients, but also lateral gradients of the flow. In this case, you only have lateral gradients of the exchange flow, of the wind-driven exchange flow, right? Here you have both vertical gradients and lateral gradients. And here you have mostly vertical gradients, that is downwind flow at surface, upwind flow at depth. And the only thing we've changed from solution to solution here is the bathymetry. So the shape of the bottom will have a lot of influence in how the flow responds, the fluid responds to wind forces. This would make sense, right? Because it's approaching a channel with flat walls on the sides. So it would make sense that you have downwind flow at the surface and upwind flow underneath, at two vertically sheared wind-driven exchange. Okay, any questions about here? Remember, we're talking about homogeneous water here. So this is only the wind-driven flow, part of the flow. Now, what kind of dynamics are we missing here from this momentum balance? What terms are we neglecting? You have the dynamics are written down right there. We're missing Coriolis. What else are we missing? Do you think Coriolis will be important for the wind-driven circulation? No? Yes. Maybe. Sometime. Well, we'll see in a minute.
Direction.
We're missing advection. That's right. And what else? That's practically it. We're missing the local changes also. Right? But these solutions are at steady state. So if we disregard those, the local accelerations, the du dt or the dv dt, then we're okay. But we're missing maybe two important ingredients, Coriolis and advection. Right? So now we take a numerical model and we look at the triangular cross-section of Wong and of the previous solution, and adding the effects of rotation and also the effects of advection. What happens is that you still have the downwind flow. In this case, the wind is going away from us. That's what this symbol represents. And yeah, let me backtrack a little bit. We're looking at two cross sections here along the channel. So this is close to the head of the channel, where the channel gets close, and this is in the middle of the channel, this solution. So what we get, the colored contours here represent the along channel flow, and the arrows represent the cross channel flow. So we're looking at the cross channel flow also, not only the along channel flow in these solutions. So let's look at what happens in the middle of the channel, midway along the channel. So you have these red areas represent downwind flow, and the blue areas represent flowing upwind flow. So the red areas are water going away from us, and the blue areas are water coming in. This is consistent with the analytical solution, the theoretical solution. Where you start seeing a little more detail and more effect are in these cross-channel flows. With no rotation, there are no cross-channel flows. These arrows would be effectively zero. The white arrows would be effectively zero with no rotation. So with rotation, think about it. The wind is blowing into the screen. So at the surface, in the northern hemisphere, what's going to happen at the surface? It's going to be deflected to the right. So that's what you see in the arrows at the surface, right? So on your right-hand wall, the water will sink, and on the left-hand wall, the water will upwell. So you get a cross-channel gyre that is clockwise in our point of view here. In our point of view would be clockwise, as you see here, to the right at the surface, and then, so it's a clockwise gyre. And also because of nonlinear effects, you have this smaller scale smaller scale gyres. So you have the basins, the wide, basin-wide gyre, clockwise gyre, and then two smaller clockwise gyres too. So those are the effects of rotation. Again, the main effect of rotation is to produce this clockwise gyre, and the effect of the advective terms is to produce this smaller scale advective. This is the solution at the head of the basin, but we're not going to talk about it. The water is all converging there. So, all right. So those are the very important effects. A way to visualize the effects of rotation very nicely is through these representations. What we have are particle trajectories looking at the channel here, looking at it from above, from an airplane. So in the XY plane, and we have the particle trajectories that they would fall. The particle trajectory is produced by a wind that's blowing toward the head of the basin, toward the close end of the basin. This would be the cross section right here at the mouth of the basin. The cross section in the ZY plane. So do we understand what we're looking at here? So notice here, look at the particles, what happens. Over the shallow part, this is a cross section, so we have the blue and the green are over shallow parts. They move downwind, they hit the wall, they sink, and then they come back in the channel. Same here on this side, the solution is symmetric, or the distribution of particles is symmetric. You have downwind flow, and then sinking and upwind flow here. So looking at it in the cross section, this is what they would do. When they hit the wall, they sink, and then they come back at depth. All right, so that's relatively straightforward. But now when we add the effects of rotation, things get much more complicated and also much more beautiful. Right? Look at this beautiful trajectory. So if you're on the right-hand side of the channel, like the blue particle, has a short trajectory inside the basin. It goes like this, and then it sinks, and it goes out. So it has a short trajectory compared to this blue trajectory. So the residence time of this one is short. But compare the black one now. The black one, if you're on the left-hand side of the basin, it gets very complicated. When it hits the wall, it sinks, and it comes back and forms these stylized L's and comes out. But it takes much longer for that black particle to be in the basin than with no rotation effects. So the effects of rotation are quite important in altering the residence time of particles in the basin, and it will very much depend on where the particle is in the basin. So this is a very important effect. Okay, so those are theoretical results. What I've shown you up to now they're all theoretical results, right? But do they look anything like reality? So let's see if that's the case. I'm going to show you a couple of examples, and you'll tell me whether it looks like reality or not. So here's one example of bathymetric effects on wind-induced flow. And this is a coastal lagoon in the mainland side of Mexico in the Gulf of California. And this is called the Guaymas Lagoon. I think I've shown you this example before. So the depth of the lagoon is rather shallow. The average depth of the entire lagoon is only 2 meters, but there's this channel here that is maintained with dredging because there's a port here, and it's maintained by a maximum depth of 13 meters. So it turns out that channel is very important for the water quality of the basin because it allows the exchange between the Gulf of California waters and the lagoon to carry out. So in this particular example, the wind is blowing from the northwest, so it's going, if you see, from land to the Gulf of California. So it's blowing offshore, and we're looking at cross sections at the entrance to the lagoon, a line that we measured right here, and we're sitting right here in the Gulf of California looking into the lagoon. So we have depth versus distance. And notice that this is less than 1 kilometer, approximately 1 kilometer wide, but yet we have a very large lateral variations of the exchange flow, and also vertical variations. The interface between downwind flow and upwind flow is this broken line. That's the zero isotac. And this is for two different measurement periods, almost consecutively, 23 to 24 of February and 25 to 26 of February. Wow, 8 years ago. So you can see here very nicely, the water column was homogeneous. So you can see very nicely the wind was blowing offshore. You can see very nicely the downwind flow here more strongly over the shallowest part, and the interface curving in the sense that the theory predicts. And when the wind was blowing more strongly, the next period you have the downwind flow here and here again, and the interface now intruding all the way to the surface. So does that look like anything that you've seen from theoretical results? More or less, right? I'm going to show you just a little later. After I show you the next example, I'll compare it to the theory of the non-dimensional solution that I showed you before. Now let me show you another example. So this example, that is the one in Guaymas Bay, illustrates both lateral variations and vertical variations in the exchange flow. Right? But it's almost dominated, mostly in this case, it's mostly dominated by lateral variation, because you have downwind flow over the shallow areas and upwind flow in the channel. Whereas this other example is vertically shear rather than laterally shear. And now we go to Chile, to the mid coast of Chile right here in the Pacific Ocean. And you're looking at a bay here that's called Bay of Concepcion. And the bathymetry you see there, so it's much deeper than the previous case. Right at the mouth we have 40 meters, 30 meters deep. Notice that the presence of this island here is very important to affect the flow. In this case, we have the wind coming from the south. It's an upwelling wind. The wind is coming from the south, typical for this area to have winds from the south. So that, again, the wind is blowing offshore. Right. So, and now here we're looking at cross sections of the two flow components, the east component and the north component. Notice that to the right of this point, to the right of this point at 4 kilometers from the origin, you have a thin layer around 10 meters deep of flow going to the west and to the north. You see that? This is north and this is west, so to the northwest. Right here. And underneath you have much weaker flow, but going to the east and south, to the southeast. So you see vertically shear flow. What's going on here that we don't see the same pattern? I think it's the effect of the island. Yeah. The lee side of the island that's blocking the wind and causing some weird recirculation, perhaps. With one line, we're not able to tell what's going on, but we can say that we're on the lee side of the island here, and here the wind is blowing unimpeded and is causing this exchange flow. If you look at the vectors, it looks something like this. So these two rows of measurements are showing downwind flow, and underneath you have upwind flow, right? So this is in contrast to the previous example. The previous example was dominated by lateral shear, some vertical shear, but dominated by lateral shear. This response is dominated by vertical shears. Why do you think that the response is different?
Steeper.
Right, much deeper, right? The maximum depth of the previous example was 13 meters, and the maximum depth here is, right, 40. So maybe 4 times deeper. So the effects of bathymetry here are not relevant. The effects of if you look at the cross section of the bathymetry, it's like a U-shaped bathtub. So the bathymetry is not influencing the exchange flow, and effectively you have downwind flow at the surface and upwind flow underneath. So if we compare these two bathymetries to this solution, all I did here was to introduce the bathymetry and calculate the d8 dx and then the u, and these are the flows that you get. And in this case, we're looking into the basin in both cases. So now that to keep you alert, this cross section has been turned over, because before here we're looking seaward, right, and now we're looking landward in both cases. So notice how in this case of Bahia Concepcion, the predicted exchange flow is similar to what we observed, except in this area because of the we're on the lee of the island. But this response in the Bay of Guaymas is very similar to what we observed. And again, this is with a simple solution with no rotation, no advective terms. So at first order, we are capturing the main physics of the problem. And it turns out that in these two systems, the density gradients were too weak to influence the circulation. So these exchange flows that we saw were mainly driven by the wind. No density-driven influences, no tidal influences either. The tidal flows are rather weak in both places.
So the wind stress in cross-sectional area dominated the flow?
So the wind stress dominated the flow, right? Okay? So remember, all this is what happens to the wind response in a homogeneous system. We'll later see how that might affect the estuarine circulation and what it depends on. We see first, at first order, the bathymetry is very important to produce either a vertically sheared exchange flow or a laterally sheared exchange flow. When you have a very weak bathymetric variations across the basin, you should expect a vertically sheared exchange flow, like in the upper panel here. And when you have significant variations, the more you approach a triangular shape, the more you're going to have downwind flow over the shallow parts and upwind flow in the deep part. Right? So that's probably the main idea that I want you to extract from this up to now. That the U-shaped flow is the U-shaped bathymetry, produces a vertically sheared exchange flow, and the triangular bathymetry will produce a laterally sheared exchange flow. Okay, so now let's talk about how these channels affect tidal flows. We've talked about how they affect wind, so we're going to talk next about how they affect tidal flows. And then after that, we'll talk about how they affect density-driven flows. And then we'll try to speculate how all of them interact, because that's where we are clueless. Well, not clueless, but that's where we don't know much. Okay, so the channels will affect tidal flows at two scales: at the tidal scale, that is within the tidal cycle, and in the longer term, they will produce residual flows, mean flows, after a tidal cycle. So we're going to finish today by talking only about how the bathymetry affects tidal flows, and I'll show you. I'll illustrate the concept by showing you examples. Well, before we get to look at this is again the Chesapeake Bay and the Delaware Bay up there. So I use this figure to show you the very complex bathymetry of estuaries. And this is typical of many estuaries, that the bathymetry is quite complicated, and that will influence the distribution of the flows at different scales all right, so here's an example of how that bathymetry affects the flows. And you have the answers of the questions I was going to ask you there, but we have a cross-section right at the entrance to the Chesapeake Bay, and again we're sitting in the Atlantic Ocean looking into the Chesapeake Bay. So we have depth versus distance at two different times of the year. This is in the spring, late April, May, and this is in the summer, July, and it's going to be more than 11 years ago. It's incredible.
I was in seventh grade.
That's scary. So you have the bathymetry here of the cross section. That's the blue line. This white line. Can anybody tell me what this? Not like that. This white region. Can anybody tell me what this white region represents? So the true bottom is the blue line. But why do I have a white region there, a blanking region? For those of you who have gone out and used the current profiler to measure currents, you should know.
If we do the interpolation, they can make near the.
When we do the interpolation, we lose that. What happened? Can we see the currents all the way to the bottom when we go out and measure with the current profiler? Yeah, we can see good measurements up to 90% of the water column, right? Why is that? Why do we lose 10%? Remember the fact that the transducers of the profiler are slanted, are in an angle, 20-degree angle. They don't point downward. So that angle causes side lobe effects, causes problems with ringing as the acoustic sound hits the bottom. If it hits directly, you don't lose anything. You don't lose any signal. But since we have an angle, it's going to lose part of the water column because of the signal that bounces off the bottom, and the one that's impinging in, they come at different angles. So that's the area that you lose. So that's what's called side lobe effect. Okay, so that was a little aside. So what we did here is we notice that the length of the transect, 17 kilometers. So it's a relatively long transect. We repeated that transect for 2 days, two days and nights, so 48 hours, back and forth, back and forth. We had, I think, close to 22 repetitions of the transect. So that allows us to fit the observations to a tidal signal or a tidal harmonic, and what we get from that fit is the amplitude of the semidiurnal harmonics, which is what we have here. This is the contour of the amplitude of the semidiurnal tidal flow. So it would be the maximum semidiurnal flow distributed at two different seasons. Do you see any particularity, any generality that you can draw from these distributions? What can you say about? Actually, if somebody asked you, tell me something about these pictures, what would you say? We're looking into the estuary, right? You'd say we're looking into the estuary. But what are we looking at? What do these distributions show? Do they tell you anything? Do they whisper any secrets to you? Or do they shout anything at you? Nothing obvious? No? What are the values of red? Or you were, yeah, 90, you have that, this is 90, 80, 70, 60. So this is 90, 80, 70, 60, 50. These are centimeters per second. And same thing, up here we have 80, 90, 70, 60, 50, 40. Here we have 60, 60.
So the flow is stronger and weak.
Okay, so that's one generality, that we have stronger flows, tidal flows here.
Especially with the
And this just turns out to be the summer. Probably this was closer to spring tides than this one. Okay, so that's something good. What else?
All number is positive or
Sorry?
all number is positive?
I'm sorry,
Is it all positive? Yeah.
they're all positive. That's the amplitude. This is the maximum current, the maximum semi-diurnal current that we observed at that time. So it's the amplitude of the harmonic. Remember the
So
amplitude.
the top winder and a flood and the bottom of the drain.
That's 48. That's 48.
It's the amplitude of the semi-diurnal oscillation. How large the semi-diurnal oscillation was during those 48 hours. What did you get in that course? Just kidding. So there's nothing that these distributions is yelling at you. Nothing. They're not saying to you, we're greater here than here. Well, it says right there. Yeah, that was bad. That I put the answer there. But isn't that message that's written here? Isn't that yelling? The reds, the commies are larger in the deepest part.
Yeah, Allison said that earlier.
They prefer the deepest part, right? Well, that's what she said.
Yeah.
But do you see that? Do you see that also that the contours follow the bathymetry very nicely, more so in the lower panel than in the upper? In the upper panel, the contours follow the bathymetry very nicely over the right half or the northern half of that section. Okay, so let me ask you, why in the lower panel the contours are following the bathymetry very nicely? What does that tell you? Or what does that whisper to you if it's not telling you very strongly or very loudly or very evidently? What is that a sign of? It's not a sign of God. It's a sign of bottom friction effects. So the influence of bottom friction caused those iso tags to be distributed like that. So it's very evident in the lower panel. In the upper panel, it's also very evident in the northern half of the transect, not so in the channel. And if you notice, if you compare the two, it's obvious that the currents were weaker here, so they felt the bottom less during this time of measurement than here. So that's why the contours are not following the bottom as closely here. Near the bottom, this 50 isotag sort of follows the bathymetry. But further up in the water column, the frictional effects are not felt anymore. And that could have been due to stratification or just the fact that the currents were weaker. So you can formulate that explanation that it's either to the fact that stratification cut off the effects of bottom friction from the water column, from the entire water column, or it was that the tidal currents were weaker altogether. So what do you do to answer that question? You go and look at the tide tables and see whether you were in spring tides or nip tides, and also look at the hydrography data that you measured and see what the stratification was like. Okay? So that was the amplitude. Now, how about the phase? And you have the answer there of what these distributions represent. But there are large differences between the deep part and the shallow part here, as you can see in terms of colors. And what that tells you is that the tidal flows in channels lag behind tidal flows over shoals. So what that indicates is that in the areas of darkest blue, the tide changes earlier than in the other areas. How much early? Well, here we have, this is 40, 30, 20, 10, 0. So it's a 40 degree phase lag between this area and the surface here. 40 degrees in 12.4 hours.
It's a bicycle thing.
It's Sorry? Right, that's a bicycle thing. I'm glad I used that analogy because then you remember. But anyway, so it is 40 degrees. If 360 degrees equals 12.42 hours, how much is 40 degrees here? You don't need to do the multiplication and division. A nice rule of thumb for the semi-diurnal tide is that 1 degree equals 2 minutes approximately. So 40 degrees is 80 minutes. So 80-minute lag in the tidal current. So look at here. This is a neat result, even though it's 11 years old. In only 10 kilometers across the estuary, you have an 80-minute lag between the current here and the current here. Right. The changes in the tidal current occur earlier, 80 minutes earlier here in this region of the cross-section than at the surface here. So you have to be very careful also when you measure, when you're thinking you're measuring slack waters in a cross-section. It might be different in different parts of the cross-section. So that's something to keep in mind. In this upper example, we have 110, 190, 80. So we have, what's the difference? 30 degrees. So it's 60 minutes. 1 hour difference between the channel and the shoal. Right? So one hour is a lot. You can miss a lot in an hour if you're not careful. So that's why we like to go and sample across and throughout the tidal cycle so that we don't miss. Well, we miss something, but so that we try to capture as much as we can. Okay, so I don't think I have the answer to this other question here. How about if you go to one location in this cross-section? Go to one location, your favorite one, where the reds or where the blues are, whatever your favorite state is, and tell me where the current changes earlier, at the surface or at depth, and why is that? Many of you know the answer without looking at the picture. At depth what? At depth what?
Why?
It changes earlier or later? At depth.
Earlier?
Earlier, right. Why?
Friction?
Right, because the answer is there, the friction, right? Weaker flows, they will respond earlier to the tidal forcing. Why is that? Can somebody else use a different analogy than the bicycle? I mean, most of you who took the class last semester know the answer, but some of you didn't, so I haven't heard the explanation for that. So Mark, can you tell AJ why the currents near the bottom change earlier than at the surface?
Tell them why. Something to do with a bicycle going uphill and one going downhill or something. And the bicycle. Go ahead and explain it. Because wasn't on your walls or something?
Yeah. Alright, so if you have a faster velocity, so you have a guy on a bicycle on like a road bike flying down, you have another guy on like a little tricycle going pretty slowly. They're going, and so one guy's going much faster. Let's say they need to turn around. The guy that's going slow just has to slow down very quickly, turn around and start going. The guy going fast has to slow way down, turn around and come back. So up here, the velocity at the surface is going faster, the velocity at the bottom is going slower, so it takes less for this velocity to slow down and turn around, and this one has to slow way down and come back.
Right.
That's what I was going to say.
That's the analogy.
Downhill, uphill.
I don't remember hills.
I don't know
Because there were no hills involved. you don't need to involve hills. So the bottom line here is that the faster currents will take longer to respond to tidal forcing because they have more inertia than the currents that are weaker. They will take less time to respond to tidal forcing because they have less inertia, so they will respond earlier. And that's what we see in the tidal currents here. Okay? Just to end today, another example of the same concept comes from two transects in where? Where are we looking at here? James River that come out to the Chesapeake Bay. And very clearly you see here the amplitude of the tidal current, of the semi-diurnal tidal currents in those two channels. Here very clearly the isotachs follow the bathymetry very nicely. And the phase shows the same. The red now represents earlier changes in the tidal flows. So you can see the very large gradients. Notice here in this very short distance, in less than 1 kilometer, we have now these isotachs are 5 degrees, so we have 55, 50, 45, 40, 35, 30. 30 to 55 is 25 degrees. So that's around 50 minutes of phase lag between the channel and this shallow part. That's quite a bit. And that's why near slack waters you have a strong convergences here. You have foam lines that develop at the edge of the channels because flows are going in opposite directions, and then you tend to have convergence and divergence. There's an animation of this concept that we won't be able to see. I didn't load it on the computer, but if you go and look at it in the presentation, you'll see that what we have is that the white arrows are surface flows and the red arrows are near bottom flows. So if you compare in one location the red arrows versus the white arrows, you'll see that the red arrows change earlier than the white arrows. And the white arrows are longer also, stronger flows at the surface than at depth. And also over this area of the channel, that's where you have the strongest tidal flows. The largest arrows over the deeper parts. You see very clearly here with the very large lateral shears. Keep this in mind because these lateral shears, as we will explain later, these lateral shears modify the dynamical framework that we have established. These lateral shears. You see the lateral shears? So if U is the flow along the estuary, I'm talking about the du dy, the lateral shears. So the term V du dy will become important to the dynamics because of these lateral shears, this paddle. And this is because of bathymetry ultimately. Okay, I think, so that's pretty much it, what we have for today.